molecule has a factorized form, which is given by an electronic factor times a translational factor times a rotational factor times a vibrational factor. And the total energy is a sum of electronic energy plus translational energy plus rotational energy plus vibrational energy. These comprise the Born-Oppenheimer approximation. We have already discussed the translational motion, the state function, and the corresponding energies. These are particle in a box problem, particle in a three-dimensional box problem. We have also discussed the rotation of a diatomic molecule and the energies. Further, we have discussed for a diatomic molecule the vibrational states and the energies. So, we are going to discuss the electronic energy and the electronic state function in the rest of this course. Let us start with the simplest molecule, hydrogen molecule. This molecule has two nuclei and two electrons. We are going to label the nuclei with the letters A and B, whereas the electrons will be labeled by electron 1 and electron 2. Graphically, we have two nuclei. One is called A, the other is called B. These are hydrogen nuclei, and as you know, hydrogen atom has a single proton with charge +1, and this has also +1. These are the nuclei. Now, the Hamiltonian for any molecule is kinetic energy of the electrons plus Coulomb interaction energy. Kinetic energy, this is the electronic kinetic energy. We have just two electrons. So the expression for kinetic energy is -1/2 del 1 square minus 1/2 del 2 square. This is the kinetic energy for the first electron, and this is for the second electron. Now, the potential energy, Coulomb potential, is can be written as electron nucleus attractions plus electron repulsions plus nucleus repulsions. The expressions here are the explicit expressions. We identify each distinct pair of charges. And the total expression for the potential energy is the sum of contributions from each distinct pair of charge. What we are doing here is we are just classifying different types of pairs. This one is electron-nucleus pairs. So, these are electron-nucleus pairs. Electrons are numbered by 1 and 2. Nuclei are labeled by A and B. So, how many distinct electron-nucleus pairs? Electron 1 with nucleus A, that's one pair. Same electron with nucleus B, that's another distinct pair. Then, second electron with nucleus A, a third distinct pair. And finally, second electron with nucleus B is another electron-nucleus pair. So there are 1, 2, 3, 4 electron-nucleus pairs. These are all attractive type. Why? Because the electron has -1 charge, whereas the nuclei have a positive charge. In this case, the charge is +1. So, our standard labeling is such that we use the letter R, small r, meaning the distance of electron to another charge. Whether the charge is another electron or a nucleus, it doesn't matter. We use the standard symbol, small r, to indicate such a distance. In this case, the distances are labeled R1A, R1B. These are the distances. This is R2A, distance between electron 2 and nucleus A, and distance between electron 2 and nucleus B. Then the expressions for the contribution to the potential energy, Coulomb interaction, is charge 1 times charge 2 divided by distance. So, the net total expression, electron-nucleus attractions, is charge on the electron is -1. Charge on A and B are just protons. Their charges are +1. -1 times +1 divided by distance. So, -1 times +1 gives -1. So I will write -1 over R1A. So this term is the contribution from this pair. Similar contributions from this pair, that pair, that pair. -1 over R1B, -1 over R2A, -1 over R2B. This expression is the contribution to the total Coulomb interaction energy arising from electron-nucleus pairs. They are all attractive because the nuclei and electrons have opposite charges. So these attractions, electron nucleus attractions. When we come to this term here, electron-electron repulsions. It means contributions from electron pairs. How many electron pairs do we have here? Just one, because there are only 2 electrons. So, electron pair only 1 pair in H2. The standard notation for the distance is still r, as in here. But now, as label, as subscript, we use 1, 2, meaning distance between electron 1 and electron 2. Its contribution to the Coulomb interaction is -1 times -1 is +1, divided by distance between the 2 electrons, R1, 2. Finally, the last term, this is nucleus-nucleus pairs. We have how many nuclei here? 2. Therefore, how many pairs of nuclei? Just 1. The pair is AB, according to our notation. Now, the contribution of this term to the total potential energy is again charge 1 times charge 2 divided by distance. We should not use the same symbol for the distance between 2 nuclei because there is a risk of confusion whether we are talking about electrons or nuclei. So we use this distance, we use the symbol R. We would use R sub AB, but we have just 1 pair here, so there is no need for AB. Wherever we see capital R, we understand it is the distance between the 2 centers, because we have just 1 pair. So, we just drop the AB symbol and simply use R. If we had a polyatomic molecule, and let's say a 3-atomic molecule, then it would be necessary to indicate the distances with such subscripts. Because if we had 1 more atom, then we would call it atom C. Then we would have pairs, AB, AC, and also BC. How many? 3 pairs. In that case, 3 distances would be required. Then we would write R, capital R. Capital R will always tell us that it is the distance between nuclei. Small r is distance between an electron and another electron or a nucleus. So this is our standard symbolism. All right. Here we have just 1 pair, so there is no need for the subscript AB. Then we would write the expression. Charge on nucleus A is +1. Charge on nucleus B is also +1. 1 times 1 divided by distance is 1 divided by R. This is the contribution from the nucleus-nucleus repulsions to the total Coulomb interaction. Graphically, on the same graph, electron is somewhere, electron 1 is somewhere around the nuclei. So let's call this electron 1. And the charge on the electron is -1, of course. And you may place the electron at any other place, like say here, this is electron 2. Then the distances involved are that distance, which symbol did we assign to it? Distance between electron 1 and electron 2. Small r, 1, 2, is that distance. Then the distance of this electron to the nucleus A is designated by which symbol? Again, small r, but which electron? First electron. Which nucleus? A. Distance between this same electron and the nucleus B is designated as R1b. Then the distance between second electron and the nucleus A is R2a, and distance between second electron and this nuclear center B is R2b. You see, showing these things, these distances on a diagram is relatively complicated because we are trying to draw in just 2 dimensions. However, the idea is very simple. You just identify all distinct electron nucleus pairs, then all distinct electron pairs, and finally all distinct nucleus pairs, and assign them with suitable symbols and write down the total expression. Okay, so what is the Hamiltonian? -1/2, this is kinetic energy part, -1/2 del 2 squared. Then electron nuclei interactions, -1/RA, R1a, -1/R1b, -1/R2a, -1/R2b. This is electron nucleus attractions plus electron repulsions, 1/R12. Finally, there is this term coming from the nucleus repulsions. Now, this term in the Born-Oppenheimer approximation, the molecular geometry is predefined. In other words, R is assigned a value. Therefore, this is just a constant in the solution of this problem. This is electronic Hamiltonian. I'm going to drop the subscript later, but in this problem, this term is a constant. Because what we do is we give R a value. For example, R, we set R equals 1 angstrom. So that the contribution of this term is a constant. Now, all the other variables refer to electrons. Electrons are moving. In other words, they are in dynamic motion. Now, this term contains variables of electron 1 only. This term also contains variables of electron 1 only. This one also contains variables of electron 1. That term, this one, R2A, and this one contains variables of electron 2 only. Now, this term is the electron-electron interaction, and as you see here, it contains distance between the two electrons, R1, 2. To calculate the distance between two electrons, it is necessary to know the values of the coordinates of both electrons. What is the expression for distance? X2 minus x1 square plus y2 minus y1 square plus z2 minus z1 squared, and then you take square root to find the distance between 2 points. This expression contains variables of both electrons, and this expression cannot be written as a sum of two terms. One term containing variables of the first electron, and the second term containing variables of the second electron. It cannot be done. Therefore, this term is the troublesome term. Electron-electron interaction. To see that more clearly, we can write this as I will call this expression H1. One indicating that these three terms, this one, that one, contains variables of electron 1 only. Similarly, I will call this one, these three terms, H2. Now we can write the full expression. This is a constant that can be added later. If this term, 1 over R12, which is the electron-electron repulsion, could be neglected, could be removed from this expression, then we would simply have H1 plus H2 in this Hamiltonian. And it would mean two non-interacting electrons moving in the field of two nuclei with +1 charges separated by a distance capital R. And non-interaction means separability. Okay, we are going to discuss that approximation, which is called the core Hamiltonian approximation. But even when we include the 1 over R12 term, the exact Schrödinger equation for this problem, it is possible to say, or it is possible to obtain some exact results about the state functions of this Hamiltonian. One result is about spin. I asked you in the examination the total set of spin multiplicities. The allowed values of spin quantum numbers are determined entirely by the number of electrons. Here, how many electrons do we have? Total spin quantum numbers, S. Maximum S is given by number of molecules divided by 2. And all other values which are less than this value in integer steps and positive values are allowed. Here, in this molecule is n is equal to 2. Please note that the spin properties are the same as in atoms and also in molecules, because it all depends on how many electrons there are in the atom or molecule. Just count how many electrons there are. So, S max here is 1, 2 over 2. And S values, this is the maximum, subtract 1, you get 0. And these are the only two spin quantum numbers, total spin quantum number for S in the H2 molecule. So what are the spin multiplicities? Spin multiplicity means 2 times S plus 1. Only singlet. And triplet. Spin multiplicities. So as far as the total spin is concerned, the situation in H2 molecule is the same as in helium atom, because both helium atom and H2 molecule has just 2 electrons. Only singlet and triplet spin multiplicities are possible when we consider all solutions of this equation for the H2 molecule. Remember, there are how many solutions of any Schrödinger equation? There are infinitely many solutions corresponding corresponding to infinitely many different states of the system. These infinitely many state functions are categorized into two types. One part is singlets, the other part is triplets. Of course, spin is related with spin variables. Now we examine the solutions here with respect to space variables. In atoms, angular momentum, quantum number L, is significant in atoms. It is significant because the L quantum number is related to the eigenvalues of L square. Eigenvalues of L square are L times L plus 1. And L is useful in atoms because L square commutes with atomic Hamiltonian. On the other hand, when we have a molecule means more than one nuclear center. The fundamental difference between an atom and a molecule is an atom has just one nucleus, all right? Whereas any molecule has, by definition, more than one nuclei. It can be shown that L square does not commute with the potential energy expression V for any molecule. L square commutes with kinetic energy part, but not with the potential energy part of any molecule because of the multi-nuclei situation. That means L square does not commute with the total Hamiltonian. If L square does not commute with total Hamiltonian, what does it tell us? The solutions of the Schrödinger equation with this Hamiltonian, these psi electronic state functions, cannot be simultaneously eigenfunctions of L square. Therefore, this L quantum number loses its significance when we come to molecules. On the other hand, Z component of the angular momentum, orbital angular momentum, and we have to indicate which direction is Z-axis. If this is nucleus A and this is nucleus B, pass a straight line between the two nuclei. The direction of this line, which passes through the two nuclei, is called the Z-axis. So you have to memorize this. Z-axis in a molecule is not an arbitrary direction. In a linear molecule, and remember, diatomic molecule is a special type of linear molecule. The axis which passes through all the nuclei in a linear molecule is called the Z-axis. Then you may select the X and Y axes as perpendicular directions to this Z-axis. But you must be careful about selecting your Z-axis. And now, with respect to this Z-axis, which passes through all the nuclei in a linear molecule, this Lz is the z component of the total orbital angular momentum. What are the eigenvalues of Lz? They are m quantum numbers. In atoms, we attach ml, the L symbol here. But because in molecules, L has no significance, no usefulness, this L is simply dropped here. We just write m. Now, the possible values of m are the same as before. What are they? Allowed values of m are 0, plus or minus 1, plus or minus 2, and so on. These are the eigenvalues of z component of total orbital angular momentum. Now, whereas L square does not commute with the electronic Hamiltonian of a molecule, z component, if the z component is defined, z direction is defined that way, z component of orbital angular momentum does commute with the potential energy expression of any linear molecule. It also commutes, it always commutes with kinetic energy. So the only thing we need to be careful about is whether a given operator commutes with the potential energy part. If it commutes with the potential energy part, as I said, such operators always commute with the kinetic energy part. That means it commutes with all terms in the Hamiltonian, and in other words, it commutes with the total Hamiltonian. If it commutes with the total Hamiltonian, then the solutions of this equation, psi functions, are simultaneously eigenfunctions of Lz also, with eigenvalues given by such quantum numbers. With eigenvalue m. Energy, electronic energy in the solution depends only on the absolute value of m. Depends on absolute value of m only. Here you see that when m is non-zero, we have two possibilities, +1, -1, or +2, -2, and so on. That means, this expression means the states with m equals +1 and m equals -1 have the same energy, because absolute value is +1. Or whenever we have two states with the same energy, which term do we use? Degeneracy. So every state with m non-zero value, +1, -1, +2, -2, are doubly degenerate with respect to space variables. Now, In molecules, the absolute value of m is designated by a symbol lambda, capital lambda. This takes place of L quantum number in atoms. In atoms, we are using the L quantum number because in atoms we have just one nuclear center, and elsewhere commutes with the electronic Hamiltonian, and all the atomic states are classified according to L values. But we cannot do this in molecules. In molecules, it's only the m. In linear molecules, of course, it's only the m quantum number which has significance. Its absolute value is designated by lambda. You see, lambda starts with which letter? L letter. So the choice is because of the situation in atoms, L and lambda. Just like in atoms, we use letter codes for the numerical values of L, S, P, D, etc. In molecules, we do a similar, we employ a similar procedure. As you see, absolute values of lambda are 0, 1, 2, 3, etc. The letter code we use are sigma if lambda is 0, pi for lambda equals 1, delta for lambda equals 2, phi for lambda equals 3, and so on, using Greek letters. You see here, the notation is, again, in parallel to the notation in atoms. In atoms, instead of lambda, we have capital L, and if lambda equals 0, we use this symbol, S, P, D, F. This is atoms. And in that case, instead of lambda, we have L value. All right? If you compare the pronunciation of these symbols, this is S, this is, say it, sigma. Starts with S. This is P, this is pi. Starts with P. This is D, this is delta. Starts with D. This is F, this is phi. So such symbols are intentionally introduced so that we can more easily remember. However, you must be careful that molecular states are different from atomic states. So the symbols for the states are different from atomic states. These are for atomic states, these are for molecular states. All right, let us give a break.